Hello and welcome to Empowered Learning. This particular video will be about even and odd functions and how we test the symmetry of functions. We will first talk about what even and odd functions are algebraically as well as graphically. After that, we will use the even and odd test to show whether a function in algebraic form is even or odd or neither even or odd. And then after that, we will go into the symmetry test, which are very similar to even and odd functions, but we also include symmetry about the x-axis. And so the reason for wanting to go here is that sometimes we need to compare or figure out the symmetry of certain relations that aren't functions. So let's go ahead and get started. So first, we want to talk about what do we mean when we say we have an even function and when we say we have an odd function. Well, simply put, we know that an even function is a function that is symmetric about the y-axis. And so one good example of that would be the function x squared, which kind of looks like this. As you can see, if this is my y-axis here, how this particular function is symmetric about the y-axis, meaning that if I took this right side here and I folded it over, where the crease in the sheet of paper that I'm imagining here would be the y-axis, then I would get this left half over here. Now, when a function is odd, what we mean is that it is symmetric about the origin. And what we mean by the origin is we actually do, and I'll just put this in everyday layman's vernacular, we do two flips, okay? Or we fold our paper twice. And so a good example of that would be the function x cubed. And so x cubed kind of looks like this. Now, in order to get x cubed, let's say we just look at this right side of x cubed, okay? Kind of looks a little bit like x squared does a little bit. Not exactly the same, but it kind of looks like it. What we mean by symmetry about the origin is that we actually do a reflection about the y-axis, and then we also do one about the x-axis. So here, if I was doing a reflection about the y-axis, this graph would look something like this on the left side. And then when I do a symmetry about the x-axis, I just take what I have up here and I flip it. So let's say I take it like that and I flip it about this axis, and this is how I get this piece right here. So that is actually what we mean when we say that a function is even or if it is odd. Okay, in particular, even is symmetry about the y-axis. Odd is symmetry about the origin. Okay. Now, moving forward here, I have some other explanations. And so, algebraically speaking, when a function is even, we say we can replace everywhere where we see x with negative x, and what we get is still f of x. Or put another way, if I plug in, let's say if I have a point x, y, and let's say I plug in negative x, I still get a positive y, okay? Whereas for odd, we have this type of relationship here, where if I plug in a negative x into f of x, I get the negative of y. Or simply put here, if I have a point xy on the graph, then I know I also have a point negative x, negative y as well, okay? And so comparing that point-wise, of course, that would make sense because here with x squared again, we know that that particular function is even. So if I took x to be -2 and 2, we know both of those y outputs would be 4. Okay. And similarly with x cubed, let's go back up here for a second. If we plotted 2 points there, we do -2 and 2 again. Whenever we plug in -2 into x cubed, we get -8 for an answer. But when we plug in 2 into x cubed, we get a +8. And so it turns out that for functions that are symmetric about the y-axis, we have this same relationship that you see right here for every single pair of points on its graph, of course, except for the point 0, 0. And similarly for the functions that are symmetric about the origin. Okay. All right, so let's go ahead and move on down to some examples. Now, how we actually test this is quite simple. All we're wanting to do is, instead of having f of x here, we replace everywhere where we see x for our function with negative x, as you see in this first example. And what we want to see is, do we get this original function back again? Or do we get the negative of the original function back again? If we get the original function back again, whenever we plug in a negative x, then we know the function is even. If we get the negative of the original function back, then we know that it is odd. And if we get neither one of those cases, then we know that it is neither. So with the example A, you see that whenever we plug in negative x into our function f of x here, that we replace x with negative x, and so of course negative x quantity cubed is just a negative x cubed, and so of course a negative x cubed times 6 ends up being a negative 6x cubed. And of course, subtract a negative x, we know that subtract a negative number is the same as addition, so that's why we have plus x here. Now if we look, and I'm going to get rid of this right quick, if we compare what we have here and here, we see that those terms are opposites. And we see here that these terms are also opposites, okay? Mainly that one term is positive, the other one's negative, okay? If we factor out a -1 out of both terms, then what we have is the negative of what we started with, which was this. And so therefore that allows us to say that f of negative x is equal to a negative f of x. Meaning, put another way, that we have a point xy on the graph, so that means we also have another point negative x, negative y for every point xy on our graph there. And so thus, from an algebraic standpoint, we have proved that that particular function is odd. Now, the reason why it's important to prove it this way versus just trying numbers is, remember, if we did it for numbers, we would have to do that for every single real number imaginable, okay? And then all the ones that are unimaginable. And of course, you nor I have that long on this earth, or does anyone else have that long on this earth to be able to do that. So what we do is we think about it in an abstract sense, and we say that let x just be any real number. And so if we plug in any real number into our function to where that real number is the negative of the one that we were considering to start off with, what do we come out with? And so that's what allows us to be able to prove this nice and easy. Now, for example B, we see that when we plug in a negative x everywhere where we see x, we come out with a situation where we do not either have the same nor the opposite of what we originally had. And so what I'm doing is I'm comparing this to what I see here after I plug in my negative x, okay? So of course, negative x quantity squared is a positive x squared. So a positive x squared times 2 is 2x squared. A negative 4x times a negative x is a positive 4x, because a negative times a negative is a positive, okay? And so now you can see that all the terms, whenever we plug it in for the original function, matches except for the 4x term, okay? So therefore it can't be even, and so that's what I'm saying here. And since we don't have negative 2x squared plus 4x minus 2, like how we see here, meaning the opposite of what f of x is, then we can't say that it's odd. So in this case, this function is neither even nor odd, meaning that there's pretty much no symmetry at all in terms of the x-axis, y-axis, or the origin. Okay. Now for the third one, C, we see that whenever we plug in a negative x in for x squared, notice that the negative that is here is actually the one that is there. And then we plug in the negative x. Okay. And you also need to watch out that you do not try to put these two together and say a negative times a negative is a positive. Reason being is because you have an exponent here. And if you remember from order of operations, you may have learned it as PEMDAS, or depending on where you live at in the world, you may have learned BODMAS. Then we know that we have to do exponents or other things before we do multiplication. And so that is why when we come here, we have a negative x quantity squared, which is just negative x times negative x, which is a positive x squared, times a understood negative 1 here. And so that's why our result ends up being like this. And of course, if we look at all this, we see that these two things match exactly, which is why we said f of negative x just equals f of x. And so with that, we actually have our three examples of how we can evaluate a function being even, odd, or neither. And so next what we're going to do is actually try some other examples on our own that haven't been worked out yet. All right, so we have a few functions here that we want to try to test and see whether they are even or odd or neither. And so we're just going to go ahead and do just like how we did in the last examples, which is just plug in negative x everywhere where we see x and look at our outcome. So to start off, we will say f of minus x is equal to 4 times a negative x quantity squared minus a negative x plus 2. And so here we know that a negative x quantity squared is just a negative x times a negative x, which is a positive x squared. And that added on that plus multiplied with the 4 is going to give us a positive 4x squared. We know that a subtract a negative number is the same thing as addition, so that would be plus, and then we have plus 2. Now when we go and compare what we have here to what we see over there, we see that this particular function is not equal to f of x exactly, mainly because this is a plus instead of a minus, okay? And of course, if we had f of minus x, and I'll just go ahead and write that right here. Sorry, minus of f of x, I mean, then that would mean that we would basically change all of the signs for each of our terms here, which would give us a negative 4x squared plus x minus 2. And we see that, of course, what we see right here does not match up exactly with what we have right there. So this would not be equal to f of negative x either, okay? So for this one, for A, the answer would be neither even nor odd, okay? Moving on to the next example, if we want to algebraically test this, again, we could just say g of negative x, and everywhere where we see x, we replace it with a negative x. And so once we've done that, again, we know that negative x quantity squared is a negative x times a negative x, which is a positive x squared. And so along with that, having a positive x squared times a negative 2 would just end up giving us a negative 2x squared. Okay? And of course, a negative x raised to the 4 is negative x multiplied times itself 4 times. Since we have negative x being multiplied times itself an even number of times, then we know that the answer is going to be positive, because that's just like having 4 negative numbers being multiplied times each other. We know that a negative times a negative is a positive. So these first two would be a positive, and then the next two would also be a positive. And so a positive times a positive is a positive. So we end up having this, and of course, we could just simply write that this way. And if we look at it, this is the exact same thing that this is. So therefore, we know that g of negative x is the same thing as g of x. Okay? So from here, we would kind of drop down here and just say, all right, this is equal to g of x. And thus, this particular function would be even. Okay? Now, for example, C, we have a function h of x, and we'll do the same thing. So h of negative x is the same thing as a negative 3 times absolute value of negative x. And so for this one, what we'll do is we'll use some of the properties about absolute value that we know here. Now, namely, here we know that negative x is the same thing as a negative 1 times a positive x. Okay? And then from that point, we know from our absolute value rules that we can rewrite this way. Okay? Well, we can split that up and say that that is negative 1, absolute value of negative 1 times absolute value of positive x. And so now we know that the absolute value of negative 1 is just 1. And of course, we keep the absolute value of x there the same. Because remember, our goal is to try to plug in negative x and see how much we can make this look the same or as the opposite of it. Okay? Now for here, we know that negative 3 times 1 is just a negative 3. And then with that, we just multiply times absolute value of x. And we see that we get the same exact thing that we started with. So this would just be h of x. So we see that h of negative x ends up being equal to h of x. And because of that, we know that this particular function is even. Okay, so now for the last one in this particular example set, what we'll do is same thing again. We will take everywhere where we see x, and we're going to replace it with a negative x. And so now we see that we have negative x quantity cubed, which is like multiplying negative x times itself 3 times. Since we're multiplying a negative something times itself an odd number of times, we know that we're going to end up having a negative result. And that's mainly because here we know that a negative times a negative is a positive, and a positive times a negative ends up being a negative. So here this would end up giving us a negative 4x cubed. And of course, subtract a negative number is the same as addition. Okay? Now, looking at this, we compare what we have here with what we have here. And if you notice, we have a negative 4x cubed here as where we have a positive 4x cubed there. So that's opposite. We have a positive x here, and we have a negative x here. That's opposite. So we know that these two are opposites of one another. And so to clearly show that, I could factor out a negative 1 out of both terms, which will essentially just change the signs of each term. And if you notice, this is the exact same thing as we had in the beginning. So we could rewrite this as just negative of z of x. So z of negative x just equals negative z of x. And so this tells us from our rules that this will end up being an odd function. Okay.